Hey guys, I'm Andrew from Lampro Event Solutions. Welcome to our first online sound training session that will be discussing the basics of sound. Please remember to follow us on Facebook and to subscribe to our YouTube channel to receive regular updates for future sessions that will be coming up in the next few weeks. If you have already subscribed to our YouTube channel, hit the notification bell to receive notifications about the latest videos. Right, before we get into the session, I would like to do a short introduction about my company. Lampro Event Solutions specialize in technical services for the events industry, and we're a supplier and installer of professional sound, lighting, and AV equipment. We make use of a number of professional brands that include Turbo Sound speakers, Allen & Heath's digital and analog mixing consoles, Audix, Sennheiser, and Shure microphones, as well as other processors that include Radial Engineering and DBX. We will be referring to a lot of these brands when doing some of the practical demos and presentations in the upcoming sessions. You will probably be making use of different brands yourself, and please feel free to do so. The theory behind these sessions will be applicable to all the makes and models of professional sound equipment. There are a few others that I might also refer to, including, believe it or not, Behringer and Wharfedale speakers, as well as Samson microphones. I'm fully aware that there might be a lot of you that are only starting out with sound and that cannot necessarily afford some of the expensive equipment. I want to encourage you that there's nothing wrong with starting out with some of the entry-level brands that are available out there. When I started my company about 13 years ago, I purchased a number of Behringer speakers, mixers, processors, and Samson microphones that I still use very effectively to this day. You don't need the best of the best to get proper results out of your equipment. The entry-level brands have their limitations, but if you know how to use your equipment properly, you can still get a good sound mix out of it. If you focus on gaining more experience and to sharpen up your skills as a sound operator or as a sound engineer, you'll be able to deliver a good service with some of the most basic systems that are available. Having the best equipment doesn't mean that you will be able to achieve a good sound mix. At the end of the day, it comes down to the skill of the sound engineer. Secondly, I just want to let you guys know about some of the references that I will be making use of during the training. As mentioned with my previous video, the most important one is the Yamaha Sound Reinforcement Handbook. And I quickly just want to show you guys what it looks like. That's the handbook over there. If you're able to get a copy of this handbook, I would strongly suggest that you get one. The publication is fairly old and was released about 20 to 30 years ago, but it's still a very good source of theory that covers all the different aspects of sound reinforcement. There are a couple of other references that I also use, which includes the Soundcraft Guide to Mixing, which you can find on the Soundcraft website, which primarily focuses on mixing consoles and how to achieve a good sound mix. The next one is Microphone Techniques for Live Sound Reinforcement that you can find on Shure's website, and that'll be discussing the different types of mics and how to use them effectively for live sound purposes. The third one is Loudspeaker Basics from electrovoice.com, and that focuses on the different types of speakers and their use. The fourth one is 10 Key Tips for Better Sound, which you can find at behindthemixer.com. And then lastly, the Alto Pro Live Sound Guide that you can find on the Alto Professional website, which will give you a general explanation of sound from start to finish. All of these publications are available for download in the video description below, so please feel free to make use of it. Right, with all of that said, let's get into our first session of the course, namely the basics of sound. When you think about it, what is the first thing that comes to mind? Well, how about asking yourself a very simple question? What is sound? Sound is a form of energy, and there are two types of energy that is applicable to sound reinforcement. Firstly, acoustic energy, which takes place by means of sound waves. In physics, sound is a vibration that propagates as an acoustic wave through a transmission medium, such as a gas, liquid, or solid. These vibrations or acoustic waves are also referred to as sound pressure waves. Secondly, electrical energy, which takes place by means of electric signals. In sound systems, sound waves are converted into electric audio signals and various forms of processing takes place. Our ears also convert sound waves into electric signals, which our brains will interpret as sound. This session will look at acoustic energy in more detail. Acoustic energy is illustrated in the picture below with a speaker on the left that produces sound waves or pressurized air molecules that the human ear on the right will pick up. The graph at the bottom is a representation of what a sound wave will look like that we will get into shortly. There are a lot of different factors that will affect the way that we hear things. Air pressure, changes in temperature, and absorbing materials has an effect on the propagation of sound waves, and it will affect the overall response of different sound waves. In cold temperatures, sound propagates downwards, and in warm temperatures, sound will propagate upwards. Different types of environments will also affect sound. This is referred to as the acoustics of an environment. Materials with uneven surfaces, for example, wood, trees, curtains and carpets will absorb sound waves. Materials with smooth surfaces such as concrete, glass, metal, etc. will reflect sound waves in different directions. This process is known as reverberation. Reverberation is commonly referred to as the echoing effect that you will hear in an empty building or in a cathedral. Here's an illustration that shows you the process of reverberation. If you have a look at the speaker or presenter on the stage, you will see that the sound travels directly to the people in the audience, but some of the sound waves will also reflect off the walls, ceiling, and other features before reaching the audience again. This will cause the echoing sound that we commonly hear in empty rooms or venues. My studio is set up in a small venue at the moment, and if you listen carefully, you will probably be able to hear my voice echoing in the background. My voice is picked up directly by the microphone, but there's also multiple reflections that take place as sound waves bounce off walls, the ceiling, and the floor. The following illustration will show you this process. As you can see there, you've got the reflective surface at the top, the sound source, which is my voice, and the direct sound being picked up by the microphone, but there's also reflections taking place off that reflective surface. Okay, so next we will be having a look at sound waves. A sound wave is 1/2 cycle of compression, which is the positive value, and 1/2 cycle of rarefaction, which is the negative value. Voices, instruments, and other mediums that produce sound are a combination of different types of sound waves with different frequencies and amplitudes. Firstly, the wavelength of a sound wave will determine its frequency, and it's measured in hertz. High frequencies have short wavelengths, while low frequencies have long wavelengths. The human hearing frequency range is between 20 Hz and 20,000 Hz. The equivalent of 1,000 Hz is also referred to as 1 kHz, and 20,000 Hz, 20 kHz. Secondly, the height of a sound wave, or its maximum displacement from its point of rest, will determine the sound wave's amplitude, which is measured in decibels. In simple terms, decibels is the measurement that is used to determine the loudness or the volume of a sound wave. Humans can listen to sound pressure levels between 0 dBs to 120 dBs before the threshold of pain or potential hearing loss can occur. Here's an illustration that shows you a sound wave with its frequency and amplitude. There's your 0 dB value, which is presented by the straight line in the center. The sound wave has a 1/2 cycle of compression, illustrated by the curve on the top of the line, and a 1/2 cycle of rarefaction, which is shown by the curve below the line. One cycle must be completed from start to finish in order for the sound wave to be heard. The amplitude or volume of the sound wave will be determined by the overall height of the sound wave in both directions, which is illustrated by the positive and negative value on the graph. The next illustration will show you different types of frequencies at a constant amplitude. If you have a look here, you will see that the low frequencies, starting at 50 Hz, have a long wavelength. If we go further up the frequency scale, the higher the frequencies get, the shorter the wave lengths become. Have a look and listen at the following video that will show you what the different frequencies sound like. You will clearly see the sound waves get shorter as the frequencies get higher. To listen to the full spectrum of frequencies, you will need a proper set of headphones or a speaker with a subwoofer. If you're making use of a laptop or a smartphone, you will probably only hear frequencies from 200 Hz upwards. This is a good experiment that you can take part in to determine if you can hear the full spectrum of frequencies from 20 Hz up to 20 kHz. Please let me know in the comments below if you were able to hear the full frequency spectrum. When I conducted this experiment on myself, I managed to hear frequencies from 50 Hz up to approximately 15,000 or 15 kHz. Generally, low frequencies from 20 to 100 Hz is usually picked up as vibrations, and they aren't really that audible. Well, from my own experience anyways. Once the 15 kHz mark was reached, it was virtually impossible for me to hear the rest of the frequency range up to 20 kHz. Contributing factors to this might be the speakers that I'm using, as well as my age. As you get older, your hearing will start to deteriorate. Constant exposure to very loud sound levels will also have a negative impact on your hearing. That's why sound engineers have to take care of their ears, which is probably easier said than done. I know it can be difficult since we all enjoy doing sound and everything that goes with it, but this is an important issue that needs to be dealt with in the best way possible. If we lose our ability to hear, then what's the point of doing sound anyways? Okay guys, so this brings us to the next illustration that I quickly want to show you. If you have a look at the decibel chart on the left, you will see a number of different decibel levels, starting from the bottom at 10 decibels all the way up to 180 decibels. Remember that 120 decibels is considered to be the threshold of pain, where constant exposure to very loud sound levels may result in hearing loss. A normal conversation at 60 decibels is considered to be an average volume that you can be exposed to for 8 hours or more. The graph on the right gives you more info regarding this. If we go further up the decibel chart to 120 or 140 decibels, you will see it's compared to the type of sound levels that you will find at the rock concert. Please keep in mind that these levels will probably occur at a close proximity, which will make them more harmful to your hearing. Right at the top of the chart, you will see a shotgun blast coming in at 170 decibels. At close proximity, this is considered to be very loud, but since the blast is very short, it will not be harmful to your hearing. Constant exposure to very loud sound levels, on the other hand, is what we need to avoid to prevent hearing loss. Right, guys, so that covers all the main topics when it comes to acoustic energy. We had a look at sound waves with their frequencies and amplitudes. Here is a video to recap most of the points that we discussed, as well as a few other interesting facts that is applicable to the subject.
Sound waves generally have four main qualities: a frequency, which determines the pitch of the note, a wave shape, which determines the timbre, an amplitude, which determines the volume, and a phase, which determines how sound waves interact. We will spend the next couple of videos discussing these qualities. If a string vibrates back and forth 200 times a second, it's causing or emitting 200 sound waves per second. And the number of sound waves that pass a fixed point per second, or the number of times a string vibrates per second, is called the frequency and is measured in hertz. So our string is vibrating at 200 hertz. When you play middle C on a piano, the frequency is 262 hertz. This means the string, and therefore the air, is vibrating back and forth 262 times per second. When you play middle A above middle C on a piano, the frequency is 440 hertz. Again, this means the string is vibrating back and forth 440 times per second. So frequency and wavelength determine the pitch of the sound. And because all sound travels at the speed of sound, which is roughly 343 meters per second through air, waves with a shorter wavelength arrive at your ear more frequently than longer waves, and so have a higher frequency. Now, the equation for speed is wavelength times frequency. So if we wanted to find the wavelength of a note, we would need to divide speed by frequency. So again, speed is 343 meters per second, and middle C is 262 hertz, so that means its wavelength is 1.3 meters. Similarly, the A above middle C is 440 hertz, which means its wavelength is 0.78 meters. So the shorter the wavelength, the higher the frequency, and the higher the pitch of the sound. Incidentally, the speed of sound actually varies depending on the medium through which it's traveling. When traveling through air, the speed of sound will be affected by the altitude, the humidity, and the temperature of the air. And sound travels faster through liquids and solids because the molecules are closer together. So sound travels at about 1,482 meters per second in lukewarm water and 6,420 meters per second through aluminium. And also keep in mind that the speed of sound is not the speed at which the air particles move. Air particles speed up and slow down as they create the sound wave. The speed of sound is how fast the disturbance of the air particles moves. So the pitch of a note is determined by its frequency, and not by the shape of the wave. Changing the shape of the sound wave while keeping the same frequency will change how the note sounds, that is, the timbre of the note, but will not change the pitch of the note. So all those sounds had the same frequency of 440 Hz, but had different wave shapes, and so sounded different. And altering wave shapes is done extensively in electronic music. This allows you to make a note sound much more interesting than a plain old boring sine wave. Now, the wave shape was altered digitally here, but acoustic instruments do something very similar. But we will discuss this in detail in a future video on the overtone series. Another interesting phenomenon is the Doppler effect. When a police car drives past you with its siren on, the pitch of the siren seems to decrease. This is because the wavelength of the sound waves emitted by the moving object are squashed in front of the object, thus increasing the frequency and the pitch of the sound. And conversely, the wavelength of the sound waves emitted from a moving object are expanded behind the object, thus decreasing the frequency and the pitch of the note. This is similar to waves created by a boat moving through water. And this is also how sonic booms are created, as an object moves faster than the sound it's creating. As an object travels faster and faster, the sound waves build up and compress together until they form a single shock wave at the speed of sound. Now, the human ear can generally hear frequencies between 20 and 20,000 Hz. This is about 10 octaves. Incidentally, dogs can hear up to about 40,000 Hz, and whales and dolphins can hear up to about 175,000 Hz. Our eardrums flex in and out as the changes in air pressure push against them. However, our eardrums can't respond properly if the ripple pattern repeats too quickly or too slowly. And just as a point of reference, the lowest key on a standard piano is the note A and is 27.5 Hz. While the highest key on the piano is the note C and is 4,186 Hz.
Okay guys, so lastly we will have a look at electric energy that was mentioned briefly at the start of the session. In sound-related terms, electric energy is acoustic energy that is turned into an electric impulse or signal, called an audio signal. This happens by means of an input transducer, such as a person's eardrum or microphone. When sound waves enter our ears, the sound waves are converted into an electric signal, which the brain interprets as sound. In sound systems, there are different types of input transducers. Microphones are the most common types of input transducers that are used in sound systems. Once the sound wave is converted into an electric audio signal, it can be pre-amplified, processed, and amplified before being converted back into an acoustic signal, which is done by means of an output transducer, namely loudspeakers. This is the primary function of any sound system, and all of these steps need to be followed to complete the whole process effectively. Since sound systems fall under the category of electrical energy, we will be having a look at the sound system or sound chain in the next few sessions that will be published in the upcoming weeks. That concludes our first session that dealt with the basics of sound. If you guys have any questions about any of the topics that were discussed, make sure to send us a message or to leave them in the comment section below. Please feel free to invite your friends and colleagues that might be interested to join us with the next few sessions that will be shared on Facebook, YouTube, and Instagram. As always, thank you, and I will see you soon.